Imagine you have all these enemies that want to attack the player, but you want to limit the number that can attack at the same time. And once one of the attacker dies, you want another one to take its place. And if the player dies, you want all the attackers to go back to their original location. So how do you implement this without having all of the enemies having to coordinate with each other, keep track of who's attacking and who's waiting, communicate with the player to get their current state, and avoid all this mess of dependencies? Well, the answer is the Mediator Pattern. Welcome everyone to the second part of this series on software design patterns in Unreal Engine. In the last video, we discussed the observer pattern and how we can use it to communicate between different objects of our game without coupling their implementation. If you haven't seen that one, I'm going to link it somewhere on the screen now. And in this tutorial, we will be discussing the Mediator Pattern. We will be covering two use cases in this video. First, I'll show you how to use the Mediator Pattern to implement a combat manager, and this combat manager will handle the combat scenario I showed you in the intro of this video. Then, the second use case, I will show you how to utilize the Mediator Pattern to fix some of the drawbacks of the observer pattern that we implemented in the last video by creating an event manager. So let's get started. So what is the Mediator Pattern and what problem does it solve? Well, this pattern aims to answer the question how to coordinate communication between different actors in my game without having direct references or dependencies on each other. If we take the example in the beginning of the video, how do the enemies know how many attackers are currently attacking the player, and if they can also attack now or not? So the mistake that most people make here is have direct communication between the enemy and the player and the enemies and each other. Not only does this create hard references, which is bad for memory usage, but also creates a dependency between the different actors in the game, which means that they both need each other to function correctly. It's always good to aim for what is called loosely coupled code, which means that separate parts of your game function independently of each other. And if you want to make a change later down the line, it's going to be a lot easier, and your code is even going to be reusable in other projects. So how does this mediator pattern work exactly? Well, the mediator pattern says that to make certain actors independent of each other, you should have them communicate only through a mediator that sits in the middle and never directly to each other. The mediator then redirects the actions needed to the correct actor. That way your actors only depend on a single mediator class and don't care what happens on the other end. Imagine the real-life use case of airplanes approaching an airport and they want to land. Now the airplanes don't communicate directly with each other and coordinate, you take runway 1, I take runway 2. No, that would cause a lot of accidents. They communicate through air traffic control, which is a tower that sits in the middle and coordinates the landing efforts of all the different aircrafts that's coming. And that's a real-world usage of the mediator pattern. So let's jump right into our first practical use case and build the combat manager. Now the problem here is you have all these enemies that want to attack the player, but you want to limit the number that can attack at the same time. And once one of them dies, you want the other one to take its place. And if the player dies, you want all attackers to go back to their original location. So instead of putting all of this logic in the player and the enemy class, we're going to create a combat manager as our mediator to handle all of this combat logic and keep the player and enemy logic decoupled. To do that, we'll first create a new actor called combat manager. And this actor is going to be placed in the world. Now, this combat manager will need to keep track of a few things to achieve the behavior we want. It will have a variable called attack target, which is just an actor reference. Then it will have a list or array of attackers, which is an array of actors. And finally, it will have an array of waiting attackers. These are the attackers that want to attack, but the max has already been reached. And note that they are all actor references. I didn't say that the attack target is of type player or the attacker is of type enemy, and this is going to be very important in a second. But first, how should the actors communicate with this mediator now? When the attacker joins the fight, they will ask the mediator if they can attack. Then the mediator will check how many attackers are already attacking the target, and then tell the attacker either yes, you can attack, or no, you should wait. This means that the attacker should expose an attack function and a wait function to the mediator, but leave the implementation up to the attacker themselves. And this is exactly what interfaces are for. So let's create an interface for the attacker, and I'll show you how it's used. So in our Combat Manager folder, let's create a new interface and call it BPI Attacker. This will contain the definition of all the functions the mediator needs from the attacker. So first, an attack function that takes as input the attack target as an actor. Second is a wait function that also takes as input an attack target. And lastly, a retreat function. This will be called when the attack target dies to tell the attacker they can now retreat. Great. Now these are all the functions the mediator will use to communicate with the attacker. Now let's create the interface for the attack target. Let's call it BPI Attack Target. And the mediator needs to know only one thing from the attack target, and that's how many attackers can attack you at the same time. So we'll create a function called getMaxAttackersCount, and this returns an integer. Okay, now before we implement these functions, let's see how the Combat Manager will use them. So back in our Combat Manager, on begin play, let's get the max attackers count from our attack target and promote that to a variable. Next, we said we need a way for the attacker to ask the mediator if they can attack. So let's create the function for that and call it handleAttackRequest. Now, this function takes as input an actor reference of the attacker. Make sure the attacker is also not the attack target. Then check if the number of current attackers is less than the maximum defined by the attack target. If true, then add new attacker to the array of attackers, and if false, we'll add them to the array of waiting attackers. But we still need to actually tell them to attack or wait, so we'll call the attack function on the true branch and call the wait function on the false branch. But notice that I didn't have to cast from actor to BP enemy, because attack and wait are interface functions that can be called on any object and won't do anything if the object doesn't implement the interface. Now this function is ready to use. All we need to do is implement our interfaces in the enemy and player and call this function. So starting with the player, let's go to the class settings, and under interfaces, we'll add the BPI attack target interface. And this will give us a function here to implement on the left. So let's double click it and just add a static number here, like 3 attackers, and that will be our max. Then we go to our enemy, and same thing, class settings, add interface, BPI attack target. Then we implement the 3 attacker functions. It's good to mention here that I have a very simple behavior tree for my enemy with 4 states: a passive, wait, attack, and dead state. And these states are all controlled by a state variable in the AI controller. And this is what we're going to be doing when we tell the enemy to attack or retreat or wait. We'll just be changing this variable through a function in our AI controller. So back in our enemy, let's double click all of our interface functions. And for each one, we will just get our AI controller and switch the state to the correct one. And the final step is to actually call the handleRequestAttack function from our Combat Manager in our enemy. And back in our Combat Manager, we need to tell it who the attack target is. So we're going to make this attack target variable instance editable. And also in the begin play, check if it is not valid. So if we didn't set an attack target from the level, we just default to the player. And now let's test it all out. All right, so right now only 3 are attacking me and the rest are waiting. Nicely done. And if I go to my character and change this 3 to something like 5, now we have 5 attacking me and only 1 waiting. Perfect. Now let's handle the case that when our attack target dies, all of the attackers should go back to their original spawn location. To To do that, let's go back to our combat manager and add a function called handleDeath. Now, this function will take as input the actor that is calling it, and it will check, is this actor the attack target? And if so, then we want to tell all the attackers and waiting attackers to retreat. We'll do that by combining both of the attackers and waiting attackers array using an append function, then loop over the combined result and call retreat on each actor, which is an interface function. Then, when the loop is complete, we empty both the attacker and waiting attackers array so that we start the encounter from scratch the next time. Now, all we need to do is call this function from our player when we die. So in our player class, let's get a reference to our combat manager and promote that to a variable. And down here, I fake death when I press the Z key. So after that, we'll just add a call to handleDeath function from our combat manager. All right, now let's test it out. So if I press Z, I'm gonna die. Nice, and they all go back to their original location. Awesome. Now, the last case we need to handle is when an attacker dies. We want one of the waiting attackers to take their place, because right now they just stand and wait. All right, to do that, we need a function in our combat manager. Let's call it engageWaitingAttacker. Now, this function gets the first waiting attacker in the array. Make sure that it's valid because maybe there are no attackers waiting. And if it is valid, then add them to the attackers array and remove them from the waiting attackers array. And finally, call their attack function. Now we just need to call this function when the attacker dies. So we'll handle that in the handleDeath function. So off of the false branch, so if it's not the attack target, we check, now is this actor in our array of attackers? Is it one of the attackers? So if it's true, that means an attacker died. So we remove them from the array of attackers and call engageWaitingAttacker function. Finally, in the false branch, let's handle the case that when a waiting attacker dies. So then we just remove them from the array of waiting attackers, and that's it. And now finally in our enemy, when the enemy dies, all we need to do is get our combat manager and call the handleDeath and pass ourself as a reference. All right, now let's test everything out in action. So we have 3 attackers attacking me. I kill one of them. A waiting attacker takes their place, and so on. Now all waiting attackers are attacking me, and if I die, they all go back. Awesome. Now I can even make one of these enemies, or really any actor, the attack target. So just by clicking your combat manager in the level and select the attack target here, let's say to be this guy. Now if I play, you'll see that they're all waiting and none of them are attacking, because this attacker doesn't, or this enemy doesn't implement the attack target interface. So that means that the max number of attackers is defaulting to 0. So if we go to our enemy, we say we want our enemy to also be an attack target, so they can either attack or be attacked. So we just tell them to implement the attack target interface. And the max number of attackers, we can make it a variable, max attackers, and we can make that even exposed on spawn. So we say this enemy has a max number of attackers of 3, but this enemy has a max number of attackers of 5. So now in my combat manager, let me select this enemy to be the attack target, and we have 3 attackers attacking him now. But if we select this guy, who I said should have 5, so combat manager, pink guy has 5, so you'll see that 5 are attacking him. Nice. And if I kill him, they all go back because their attack target just died. I can even make this poor cube the attack target. Now our combat manager is complete. Let's jump into our second use case, which combines the mediator pattern with the observer pattern from last tutorial to create an event manager. In the previous video, we wanted our enemy count in the widget to update when an enemy dies, and we wanted the door to open when all enemies are dead. So following the observer pattern, we dispatched or published an event when the enemy died, and we bind or subscribe to this event in the widget and the level. Now, this solution prevented the enemy from communicating directly with the widget or the door, but there's still a problem. We still need a reference to the enemy to bind to their on-death event in both the widget and the door. This means that in any part of your game, if you want to know when an enemy dies, you first have to get a reference to all your enemies in your level, which is not ideal because as a subscriber to an event, I don't care who's publishing it. I just want to be notified when it happens. And this is where the mediator pattern comes in. Instead of having the widget or the level bind directly to the event from the enemy, we'll have an event manager, which will be our mediator, handle all the published calls and the subscribe calls. Now, to create the event manager, we will first need to create a custom game state object, because the game state is an object that is globally accessible and is replicated on both the server and the client, so it will be the perfect place to hold the implementation of our event manager. Now, this game state object will be our event manager, so it will be responsible for dispatching all of the events in our game. So first we need to go to our enemy and delete our previous on-death event dispatcher, and go back to our game state and add a new event dispatcher here. We'll call it on enemy death. Then we go back to our enemy, and now instead we will call the dispatcher from our custom game state object. And I will also show you later on how you can remove the need to cast to the game state. Now let's go to our widget and get a reference to our game state. We don't need to get a reference to the enemies anymore because we can now bind to the event being dispatched from the event manager. And we'll go to our level blueprint and do the same thing. Excellent. So now when all the enemies are dead, the door should open. Widget is updating correctly, and the door is open. Perfect. All right, so now we still want to get rid of this initial reference where we loop to get all of the enemies to get their initial count, because we get their initial count and start subtracting it. When it reaches 0, we open the door. And also in the widget, we do the same. We get the initial enemies count so that we show remaining enemies 6, and then we start subtracting. So how do we get rid of this using the same pattern and avoid having a hard reference to our enemy? Well, what we can do is over here in our game state or our event manager, we can add another event and call it on enemy spawned. And now we can dispatch this event in our enemy whenever we spawn, and then count all the enemies spawned instead of just start with a default number. So in our enemy here, after the begin play, we're just going to get our game state and call enemy spawned. Now, be careful when dispatching events in the begin play. The actors that are subscribing to the event might not have initialized yet. So if you want to dispatch an event in begin play, always good to add a delay until next tick to ensure that all of the actors are initialized. So back in our widget, right now we loop over all of the enemies to get their length, and that will be our initial enemies count. Now we don't want to do this anymore. I'm going to delete this. Instead, we want to get our game state, which I should probably make a variable, and we'll just call it my game state and use it here as well. So now I can bind to the on enemy spawned event. Let me move that a bit. And what I can do is I can increase the enemy count on spawned. So I have this enemies count widget, integer that starts at 0. Now, anytime the enemy spawns, I can just get this number and say increment, which means add 1 to it. Oh, let's move this a bit here. And after adding 1, we need to update the text with our new enemy count. All right, so let's test this out. So I play and it starts with enemies remaining 6, and as I kill them, it updates correctly. Now I can even spawn new enemies when I press X here, enemies spawn, and you can see that the widget count is updating. Now enemies are 11. Perfect. Now we need to do the same thing for the door, because the door still starts with 6 enemies and it opens when 6 enemies are dead. So we're going to do this, remove the enemies count, the length and loop here as well, and we are going to get our game states. Let's also promote it to a variable here. Call it my game state. And we are going to bind to the enemy spawned and do an increment enemy count. Now, I know I'm duplicating this part here. A lot of people have commented, why are you duplicating? You already have it in the widget. Well, this is to have the widget and the door independent. If I reuse it, I'm coupling the door and the widget, and this is not something that we want to do. It's actually what we're trying to avoid. So this part is duplicated, and I'm going to increment the enemies count again. All right, so now we'll start at 6. Let me spawn some more. We have 8. I'm gonna kill them. Perfect. Door still hasn't opened. Door still hasn't opened, and only now does the door open. Excellent. So now what we've done is we combined the observer pattern with the mediator pattern to create an event manager in our game state, and this removed all references from our widget and our level blueprint to our enemy. So now we no longer have any references to the enemy, we just have a single dependency, which is our game state. Now I can quickly show you something that you might want to do as well, which is create a interface. So if you search for interface, to create an interface, blueprint interface for your event manager. So I'm going to call this event manager. Now, right now, I'm just dispatching the events here. And that means that the enemy needs to know that there exists an event called on enemy death, and we actually need to cast our game state to my game state before being able to use it. If you want to avoid doing this cast, an interface will help you with that. So if I go to my interface and I define a function, call it publish enemy death, and we have another one called publish enemy spawned. Let's compile that. So now in our enemy, I don't need to cast anymore off of the game state itself. I can show you here. So instead of using my game state, I'm just going to use the regular get game state and say publish enemy death. So now I'm calling this function on the interface, and I actually don't need this anymore. Don't need this, and I can just say here, get my game state, and publish enemy spawned. Now, the only downside of this is that in your event manager, in your game state, first of all, we have to implement this interface. So go to class settings, under implemented interface, search for your event manager. And when you compile, you'll see that you have publish enemy spawned and publish enemy death. Now you have to implement these. And the implementation is basically calling their dispatcher. So publish enemy death will call on enemy death, and publish enemy spawned will call on enemy spawned. So that's the only downside, is you'll have to sort of do this overhead part where the event dispatches the event dispatcher, but it makes your publisher cleaner. For the subscriber, you still have to cast to my game state because you need a reference to the actual published event, and you can't add that to an interface, in blueprints at least. Great, now let's quickly summarize everything we've done. The mediator pattern can be used to reduce or completely remove chaotic dependencies between different actors or objects in your game. We showcase that by creating an event manager in our game state that allows any actor to subscribe to an event without referencing the publisher of that event. We also created a combat manager as a mediator between multiple enemies and their attack target to coordinate their attacks and communicate with each other. That way, all the logic of handling coordination of the attack is taken care of by the mediator, and the attack target can just worry about implementing their attack functions, their wait functions, and just the implementation that is only relevant to them. Now, this gives us a loosely coupled architecture with excellent separation of concerns that makes our game logic much easier to scale and reuse. I demonstrate that by changing the attack target to be one of the enemies or even a cube, and everything still worked fine. Now, if you're still watching and you're still wondering why do all of this, what's the real benefit of implementing proper software design patterns, let me leave you with this. Contrary to what Hollywood movies will have you believe, programmers don't spend the majority of their time furiously typing on a keyboard. Actually, as a programmer, the majority of your time is spent reading and reasoning about your code. No matter how smart you are, your brain can only fit a certain amount of information at the same time. That's why skilled programmers are those that can write software that is easy to read and reason about, making them much faster, more efficient, able to process more information, and build much scalable products. Knowing design patterns and how to use them is how you'll be able to do that as well. Now, we've reached the end of the video. There will be more design patterns coming soon, more Unreal Engine tutorials, just a lot more stuff here on the channel. So if you're interested and you found this content useful, please consider giving a like and subscribe. And as always, thank you for watching, and I'll see you in the next one.